Let's use the first and second derivative to sketch this rational function 2x minus 1 divided by x squared. So let's give ourselves the first derivative. We have a quotient rule here. Actually, you know what? You might be able to avoid the quotient rule by rewriting this as 2x minus 1 times x to the minus 2, and then distributing that x to the minus 2. So you end up with a 2, if I have 1x, but then I take away 2, so 1 over x there, and then minus a 1, so an x to the minus 2. That gives us a 2 times x to the minus 1. I guess I could have done that anyway. Minus an x to the minus 2. That's going to differentiate, which is the power rule. So the derivative of that is going to be minus 2 x to the minus 2, and then plus a 2 x to the minus 3. All right, let's clean that up just a little bit. This is going to be minus 2 over x squared plus 2 over x cubed. This is going to give us, let me switch those around. Yeah, that just looks better. And then let's give that fraction an x on top and bottom. So now I have a common denominator. This is going to be 2 minus 2x over x cubed. Cool. So that's my first derivative. And the first derivative can change sign either at zeros or discontinuities, which would mean my original function changes direction. So it might change from increasing to decreasing. This is not going to exist at x is equal to 0. This is going to equal 0 when the numerator is equal to 0. That's when x is equal to 1. So let's give ourselves a little sign chart. In fact, let's do it up here. And we'll try to keep a tally. We'll put all of the relevant information for our graph up there. So let's put our first derivative, f prime, see what that implies about the original function. And the first derivative might change sign at 0 or at x is equal to 1. All right, we need to give ourselves some test values. So let's look at minus 1, 1/2. Ooh, bad 2. 1/2. And let's say 2. So if we evaluate our first derivative at minus 1, we get a minus 4. So let's complete the table as we go. The first derivative at minus 1 is negative. So it's negative across that entire interval. So everything to the left of 0 is going to be decreasing. If we evaluate our first derivative at 0.5 or 1/2, we get a positive number, 8. Positive first derivative means positively sloped tangent lines. Our function is increasing. And our first derivative at 2 gives us minus 1/4. That's negative. Our function goes back down to decreasing. Okay. Now that our first derivative has told us about the increasing or decreasing of our function, let's go to our second derivative. So our first derivative is right there on the right. Oh, wait, no, that was us just rewriting the function. See, this is why it's important to label your work. All of those equal signs are about f of x. So now f prime of x, let's just differentiate this. Minus 2x to the minus 2 plus 2 x to the minus 3. And our second derivative will then be positive 4 x to the minus 3 minus a 6 x to the minus 4. So let's rewrite that. 4 over x cubed minus 6 over x to the 4th. Let's give the first fraction an x on top and 1 on bottom, so I have a common denominator. Second derivative is 4x minus 6 divided by x to the 4th. So it is going to change sign, possibly, at zeros or discontinuities. There's a big non-removable discontinuity at x is equal to, or sorry, because of the x to the 4th. So at x is equal to 0, and there is a 0 from our numerator when 4x minus 6 is equal to 0. Solve that. For x, you get 3 halves. Right? If x is equal to 3 halves, the 2 cancels with the 4. You end up with the 2 on top. 2 times 3 is 6. 6 minus 6 is 0. Cool. So let's do the exact same thing. Let's look at our second derivative and what that implies about the original function. And it might change at 0 or at 3 halves. Can't draw 3s. 3 halves. There we go. All right, some test values. Let's look at minus 1. 1 would be easy to plug in, and 2. So if you plug not into your first derivative, but into your second derivative, minus 1, you're going to get negative 10. It's a negative number. So second derivative gets 2 negatives. That's just for fun, because then you're concave down and you get a little frowny face. The second derivative at the next test value, something between 0 and 3 halves, is 1. That's going to give us a minus 2. So we're still negative, concave down, frowny face. Our second derivative at 2, so what's going on the right side of 1.5? We get 1/8. That's a positive number. Our function is concave up, so we get a smiley face there. Okay, I think we are ready to plot some points onto the function and then go ahead and fill in the gaps. So our original function, first, it's going to have a vertical asymptote at 0. So we are not allowed to cross the y-axis here. We're not going to have a y-intercept. If we set our function equal to 0 and see where we're going to cross our x-axis, let's solve that. That's going to be when 2x minus 1 is equal to 0. So that happens at 1/2. So if I zoom in here, there's 2, there's 1, 1/2 is somewhere right there. We have a 0. Okay, let's talk about end behavior. So the limit as x gets larger and larger of our function. So I won't rederive it now. Go back and read the limits at infinity section inside the limit section of the notes. But this is the degree of the denominator is heavier than the degree of the numerator. This is going to get dragged down to 0. And let's look at positive x values. So in fact, maybe I should just go through this. This is limit as x goes to infinity of 2x times 1 minus 1 over 2x over x squared. Our x's cancel. And we're left with a 2 over x times 1 minus 2 over x. This approaches the value of 1, so it's bounded. What's happening to that function? it's positive for positive x values, and it shrinks down to 0. Right, so we know we do something like this. We get closer and closer to the x-axis, but positively. And what happens to 2 divided by x for negative x values? It also gets smaller and smaller, just negatively. Right, so we're going to approach our x-axis from below over there. Okay, now let's go back up to what our function's doing. So we knew we were decreasing on the left side of 0, and notice we are decreasing. We also know that we have that vertical asymptote at 0. So we're going to decrease all the way to x is equal to 0. Okay, what's happening on the, oh, let's double check our concavity. It looks like we're concave down, right? Our concavity on the left side of 0, yep, supposed to be concave down. So everything makes sense so far. What's going on between 0, so x is equal to 0, and the 0 of our function? All right. Let's see, are we increasing or decreasing? We're increasing on the right side of 0, and we're increasing all the way until we hit 1. So we're definitely increasing until we hit that 0 right there, which occurs at 1/2. What's our concavity like? Our concavity between 0 and 1.5 is concave down. So we've got that vertical asymptote. We approach minus infinity on the right-hand side of it. And I don't like that. I need to be a little bit closer. And we're increasing, but concave down. Okay. We hit that 0, and what are we going to do? We're still increasing until we hit 1. And we're still concave down. So we're still going to increase until we hit 1. Where's that? Somewhere right there. In fact, we know where's that maximum going to be? At x is equal to 1, right? Because we go from increasing to decreasing, and our function exists there. Right? We have a 0 of our derivative. So I know when x is equal to 1, I should make this more rounded. We're going to be a hilltop. And then what's going on the other side of 1? We are decreasing forever. So we don't have to revisit our first derivative. We're going to be decreasing for the rest of the way. But we're still inside this region until we hit 1.5. So we're still concave down. Until we hit 1.5. And then we switch to concave up. There we go. All right. That's a pretty good idea of what the sketch of the what the function is going to look like without a calculator.